Welcome back to the classroom. My name is Mr. Wong. Today we'll be covering Year 10 Earth and Space. The title of this lesson will be on the scale of the universe. So we're going to look at why images like the one you see in front of me here aren't a very accurate depiction of what our solar system is, and then we'll look to use that also to then give proper scaling to the planets and other objects in our universe. So let's get started. So the lesson intention for today is to use models to describe the difference in size and distance of various structures in our universe. We want to develop a model to show the differences in size and the distances that separate the celestial objects of our universe. Just a quick recap, you might remember that in our universe we have a cluster of galaxies, and in our galaxies we have things like planets, comets, asteroids, and stars. And depending on where you are in the universe, those planets and asteroids could be rotating around stars, giving us our solar systems. So putting our solar system to scale. So the image you see below provides you a simple interpretation of our solar system. We have the sun, we have the 4 terrestrial planets, we have our gas giants, we have good old Pluto. But there are quite a few errors in this actual diagram. Taking away the fact that Pluto isn't part of the planets, it's in the Kuiper belt, and we don't have the asteroid belt. The sizes of these planets are not to the correct scale, and also the distances between the planets are not to the correct scale either. So if we actually have a look at the proper scale, and I'll show you a little animation at the end to finish this off. Stay tuned for that. If we compare the size of planets, Earth and Venus have a relatively similar size to each other. Mars, as you can see, compared to Earth, is that. We also have the moon. Can't quite see the text of where it is, but you have the 4 planets of Jupiter, or the 4 moons of Jupiter, as you can see here. They are relatively similar in size with Mercury. Okay, you can also sort of see in terms of the surface level the size of the United States and Asia compared to these planets here. Okay, so if we look at the first image that we saw, this image here, relatively similar in terms of the sizing with the terrestrial planets, but not so much when we compare it to the gas giants. If we then compare it to our gas giants, you can actually see Earth is this little dot here, and that's the size of Jupiter and Saturn. If you recall what we demonstrated in the very first image of errors, Earth had a relatively similar size as Jupiter in our first original diagram, as you can see here. So that's one of the inaccuracies that we have. If we look at in terms of the radius, so how far or how wide is the planet from its center. So what we mean by radius, if we have the center point, it goes from here to here. This is what it's measuring. As you can see with Jupiter, it has a really large radius, and this is in kilometers. Compare it to Earth, our radius is much smaller in comparison to that. So it's about almost 10, 11 times bigger than the radius of our planet there. Okay, you can also see in terms of mass, there's quite a massive difference. Okay, for those who don't know what these values represent, it is what we call scientific notation. So these are actually incredibly large numbers that we can actually designate to show for how many zeros are behind these numbers. So what you can see, 27, it means that we can move our decimal point by 27 positions. Okay, so scientific notations are used to, you could say, shorten down really large values. The very first one we're going to look at, though, is what we call prefixes. So instead of saying, 1,000,000, 1,100, yada, 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 we tend to like to use prefix when it comes to express the quantity or the amount of a particular measurement. So particularly in space as well, because size and distance are incredibly large, prefixes are usually used to give you a easier explanation of how far something is, how large something is. So the most common one you'll see is the kilo. So if we use gram as our standard, a kilogram, if you actually see here, is 1,000 times greater than your average unit here. If we look at the reverse component, we have the decimal, we have the millimeter, so milli. If we had milligrams, that would be 1,000 times smaller, so 1,000 times larger in comparison to what we have here. And if we went to the milligrams, we are actually going 1,000 times smaller. So that's kind of how we express how large or how much quantity we have of something. We can use prefixes. So using this example we have here, try and rewrite the following values in a more conventional unit. What we mean by more conventional unit is this one here. Okay, so this unit here is newtons, which is for force. A is for amperes or amps, that measures electric current, and pascals, that's actually to measure pressure. Okay, or we should write electric current. Okay, so I'll demonstrate what I mean by trying to convert them into more convenient units. Okay, so 583, we have 1, 2, 3, 4, 5, 6 positions. We could use mega. Okay, so if we use a prefix like mega, it has a multiplier of 10 to the power of 6. So we can take up, so if you imagine we start our decimal here, the 10 to the power of 6 means we can move our decimal in this direction 6 times. 1, 2, 3, 4, 5, 6. So we get a value which is 10 or 58.3 mega newtons. Okay, what that means is it's the same thing as writing this, 58.3 times 10 to the power 6 newtons. Okay, so these two values mean the same thing. The one I have up here is actually expressed in scientific notation. We'll do some questions on that too. Or we can do it in a prefix like so. If I was to write this out, I'd call it a mega newton. Okay, if for example this one here, so I want to move the decimal backwards like so. I'll move it back 3 positions. You can move it back a bit more than that, but we generally like to have 1 or 2 values in front of the decimal, and we kind of just leave it as it is. So if I move it by 3 positions, if you actually have a look on my chart here, that's 10 to the power of minus 3. So I'm moving my decimal backwards by 3 positions. If that's the case, this is going to be 7.48 milliamps. Well, I can just rewrite it like this, milliamps. And so that's how you do this one here. I'll let you try and work out this one. Let's try and do this one here. So rewrite the following values in terms of their base size units. So what we mean by that, this one here is 4 meters. This one here is newtons. Okay, you can see we have, can ignore that one, we have meters and newtons. So let's look at what this prefix is. That is nano. And we have 10 to the power of minus 9, which means that, say if we have a decimal point here, we need to move this decimal point 9 times to the left-hand side. So maybe I'll just make that very clear. If you get a negative indice, it means decimal point or decimal moves left. If we get a positive indice, the decimal moves to the right. And what we mean by the base unit, so the base unit we want at the end is in meters. So we're going to express this in meters. We're going to express this in newtons. And in this case, we need to write down the amount of zeros that we have essentially. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, and then 9. Okay, so our decimal is this point here, which means we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so if I redraw that out, so 1 0 in front of our decimal, and then we wrote 1, 2, 3, 4, 5 zeros here. Then we have our value like so. You need to do the exact same thing over here. So you have your decimal point. This is in, or actually, so do the exact same thing. This is in kilo newtons. So kilo is on the opposite side. That's 10 to the power of 3, which means according to what we wrote earlier up here, if the number is 3, we need to move the decimal 3 positions to the right. Okay? So just write the number out first and then you can change it. So 450, there's our decimal, goes 1, 2, and 3. Okay, so our final number would be 450,000 newtons. Okay, so I'll get rid of that. So this would be my final number there. Okay, so if you didn't quite get that, replay this section of the video. If you're comfortable, let's move on. All right, the next bit we want to talk about is the distance between the planets. All right, so this is a much better depiction of the distance they have between the sun and between us, but we'll go into a bit more detail. There are still a little bit here and there that we can fix up. So in our original diagram, all the planets were positioned almost side by side. Now, Jupiter is a very large planet. If it was directly side by side with us, we'd be seeing it very large in the sky, but that's not the case because of the distancing they have in between each other. So let's look into what that actual distance is, and then we'll get into a new set of units to express that. Okay, so if we actually have a look, this is how far each planet is away from the sun. Obviously, the sun is up close to the center of our solar system, so it has a value of 0 or not applicable because it's the thing we're measuring it against. We have Mercury, Venus, Earth, and Mars, so you can see where they are. Relatively speaking, they're much closer to each other than the gas giants are. And you can see there's a massive difference in distance between Mars and Jupiter, which this chart that we have here gives a better scale to in comparison to the original diagram we used. So we can see it here. But one of the issues is when we express these kind of numbers, as you can see, there are a lot of zeros in these values. And generally speaking, having a lot of zeros makes it quite difficult to write out, really difficult to express. So there are actually easier shorthanded ways of expressing the size or the distance of something instead of needing to write all down all these zeros. And that is actually using scientific notations. So you can see here, scientific notations is just a much neater way to express really large or really small numbers. Okay, this in a way helps us express the product in terms of powers of 10, or you can simply think of it as the number of zeros that are in front or behind a specific value that you're looking at. And so that's what scientific notation is. If we look at this chart here, the value we have in scientific notation is 4.25 times 10 to the power of 6. Okay, so this 6 here means we can actually times, or we can add, so, or move the decimal. So it actually means we can move our decimal 6 positions to the right. So this number here is exactly the same number here, firstly, but this is a much this is like a shortcut way of expressing the same value in a smaller kind of time frame or smaller expression. So if my decimal point is just right after this 0 here, and I move it 6 positions, okay, obviously what we said, you can move it 6 positions to the right, means this one can move to the right. But just to show it is 6 positions, or it is the same number, we'll do the reverse. So 1, 2, 3, 4, 5, 6. So that's how you get from here to express that. And you'll find the exact same thing if you were doing this value here. So minus 5 means that this decimal point has been moved by 5 positions. So 1, 2, 3, 4, 5 here, okay? If I was to rewrite this into this, then the -5 means the decimal has moved 5 positions to this side here, like so, okay? So what we know is this 4 here represents the total amount of zeros that needs to be written on or moving the decimal to the right. Let's just do that again. All right, so to answer this question, remember this 4 here, or if it's a positive indice, it means that the decimal has to be moved 4 positions to the right. So if we go 1.5, it goes 1, 2, 3, 4. So this is our decimal here. We have 1 0 here, 1 0 here, another 0 here, and then decimal, and then we can write another 0 if we really want to. So it's 15,000 newtons. This one we move positions by 3. So I'll just do this quickly. 0.003145 joules. Okay. This one here, it's 6 positions. So I'll let you work that out. I will upload answers later on. And then we write the scientific notation of these values here. So assuming our decimal is here, we go 1, 2, 3. Let's just use the first number as the number in front of the decimal. Anywhere else doesn't really matter. So it's 9.215 times 10. We moved it by 3 positions. So it's like that. And we did move the decimal. We can move the decimal in this direction, so it's a positive value there. Next one we have 3.2498 times 10. Let's see how far we move the decimal. 1, 2, 3, 4, 5, 6, 7, 8. So moved it by 8 positions there. Okay. Try the next one here and see what you can get. So the next thing we can talk about is the concept of light years, light minutes, light days, stuff like that. So the speed of light approximately travels at about 3 times 10 to the power of 8 meters per second. This one is in kilometers per second, so one of the prefixes we use. So this is roughly the speed of light, okay? We talked about this before. For light to travel from Earth to the moon or the other way around, it takes about 1.29 light seconds. So light takes about 1.29 seconds to travel there. Earth to the sun, 8 light minutes. Earth to Mars, 12.7 light minutes. Earth from one side of the galaxy to another, about 52,000 light years. Now the reason why we use light years instead of kilometers is because light is really, really fast. And it travels an incredible amount of distance for a specific time period. So where our universe is incredibly large, using kilometers or using other prefixes doesn't really describe how big, or it doesn't give us a standardized measurement of how far everything is away from each other. However, because the speed of light is constant, we can actually use the distance traveled by light as an appropriate measurement or ratio to compare how far certain things are from each other in our universe. As a matter of fact, if we look at how far light travels in 1 year, that's how far it travels in terms of kilometers. If we want to write it in scientific notation, we can write it like so. 9.46 times 10 to the power of 12, right? As you can also appreciate here, saying this value here is obviously a lot easier than saying that value there. So that's how we use it. If we actually look at the total distance for light to travel to the nearest star, so if you talk about our nearest star, which is 4.3 light years, in kilometers, it's roughly 4 times 10 to the power of 13 kilometers from Earth. So that's an incredibly large value to look at in terms of distance. So it can be a lot harder to put it into a number that people can understand in context. So if we use a standard unit of measurement that is constant, then this is a lot easier to picture out. So that's kind of how we use the light years there. So that kind of concludes what we want to show in this lesson in terms of scaling the universe and the different ways we can actually measure out the solar system, different parts of the universe, and all the different structures. What I just want to end this video on is a nice little animation to show you how far the Earth goes, or how far our universe goes, and all the little bits and pieces inside of it. Anyhow, thank you for joining for this lesson, and I'll let the animation do the rest of the talking.